I'm Professor of Physics at Williams, and this is the first in the 2-lecture series, The Physics of Musical Sound. This material is something that's been interesting to me for pretty much my whole life. I've always loved science, and I'm a terrible musician, but I love to listen to music. You'll notice a little bit of a prejudice towards string instruments in this talk. So the first question we should find out about is, what is a sound? So a sound is a wave that moves through air. So my voice is coming to you right now by shaking the air. To think about that, we should start by thinking about what a wave is. So a wave is some kind of a disturbance. I'm going to create a wave for you right now on this long machine. And to create a wave, you somehow have to take something that's resting at equilibrium and disturb it. So let's disturb this guy. So you'll notice that as I disturb this machine, there's something that moves from the bottom where I'm shaking it up to the top and then comes back. But the thing that moves is not the individual particles. This bottom rod doesn't pick up and fly up to the top, right? It's the disturbance itself that's moving up and down. And that's the characteristic of a wave. It's a disturbance that moves, but the individual pieces of stuff just move back and forth in place. So a sound wave, what's disturbing in a sound wave? A sound wave is a disturbance of the air. So an easy way to think about this is to make the simplest sound I know how. Okay, let's clap. What am I doing? I'm taking my hands and I'm squashing the air up. And if you can imagine all the air molecules in here, I've actually squished them together so there's a compression. There's a region of the air that's no longer at rest, no longer in equilibrium like this, but actually disturbed because I've taken it to a higher density. And that compression moves out to you and eventually it shakes your ears. Let's see if we can see that happening. Okay, so this is sort of a visual of what a sound wave would be. It's a little region of compressed air. And we can see when we have one by measuring it, for example, on a microphone. So you can see as I'm talking here that there's some sort of wiggles happening on this screen. What is this screen? So what this is the signal coming out of the microphone, and what you want to imagine is the little compressed region of air coming up to the microphone and actually pushing physically on a little membrane, and that motion of the membrane is translated into what you see on the screen. So here's me clapping, and you can imagine the compressed air coming up and pushing, and then you see the signal on the screen. So what allows a sound wave in air to travel from one place to another? Certainly we don't have metal sticks connecting each of the molecules in the air, allowing them to push on one another. But the molecules do move freely, and so when I get some of them moving faster, if I squash them, they run into one another, and it's that collision between the air molecules that allows the wave to move from one place to the next. So that means actually that the speed with which sound propagates from one place to another depends on the properties of the air. So you might have seen somebody playing with helium. Have you guys ever seen someone breathe in helium and then their voice changes and it gets all high and squeaky? That's because when you replace regular air with helium, the air gets lighter. And we know that whenever you make something lighter, the wave or the disturbance can propagate more quickly. So the speed of sound in helium is faster than the speed of sound in air. That's how your voice gets squeaky if you play with helium. You might also know, particularly if you play a wind instrument, that the pitch of the instrument gets messed up if you've been keeping it outside in the cold and then you bring it inside to play. Again, that's because the temperature of the air affects the speed of sound, because that affects the density of the air and that affects how easily one molecule can run into the next. So for our purposes, we'll mostly be thinking about sound waves in room temperature air, and those go about 340 meters per second. So when I clap, that compression moves out to you, and in 1 second, it gets about 300 meters. Okay. Now for musical sounds, we're most interested not in waves or disturbances that just happen once, like that clap where I just create one compression in the air. We're more interested in waves that happen repetitively, over and over again, repeating the same series of compressions. Those are the kinds of waves that we're most interested in when we're thinking of sounds that have a pitch. And those kinds of waves are created when some kind of instrument or your voice somehow shakes back and forth repetitively. So that will create a series of compressions, one after the other. So I think one of the easy kind of instruments to think about for repetitive shaking is a drum, right? So what we want to do is, if we're going to create a repetitive series of compressions, the face of the drum is going to move out and squish the air, and then it'll slosh back and suck back on the air. It'll squish out and compress the air again. And so the net result you get in that case is this sort of periodic, repetitive set of compressions. So I can show you a little clip of that happening. Okay, so there's a tuning fork, one of my favorite instruments, and you can see that every time one of the prongs of the fork moves, it creates one of these compressions, and then the compressions move out, again in our case for the room, about 343 meters per second is how fast they move. Okay? So you should keep in mind, we've been talking about compressions because we're imagining squishing the air, because we have a finite amount of air to work with. If we squish this and make it extra dense, then there's going to be less left over at the edges. So what we actually end up with these periodic waves is a series of compressions and then what I'm going to call rarefactions. So areas where the air is extra dense, separated by areas where there's not as much air as usual, high density and low density. Okay, so to describe one of these repetitive or periodic waves, there's a couple of ways to think about it. Probably the most straightforward way to think about it, and the way that connects most immediately to music, is to think about how many of these compressions come to you each second. Okay, so if the tuning fork is shaking back and forth, let's say 100 times every second, it's going to create 100 of those compressions every second, and they're going to all fly over to your ears. So they'll shake your eardrums 100 times a second. So that number of compressions that come to you or are created by the instrument each second is called the frequency. It's just a number per second, and we measure that in hertz because we like to name things after famous people who discover them. Okay, so we measure them in hertz. So if I say something is oscillating at 100 hertz, it just means it sloshes back and forth 100 times a second. So one question we could ask is, what sorts of frequencies of sound waves are we actually able to hear? I mean, we could shake the air back and forth 1 times a second, or 10 times a second, or 1,000,000 times a second. Not all of those things actually represent sounds that we can hear with our auditory system. Although our auditory system is actually pretty flexible. So we can hear sounds, perceive sounds with our ears that shake the air somewhere between 20 hertz, so 20 sloshes per second, that's the lowest note you can hear, and 20,000 sloshes per second is the highest note you can hear. Okay, so that's a pretty good range. As you probably know, dogs can go up much higher than this. Actually, if you slosh the air slower than this, slower than 20 times per second, if it's sloshing enough, you actually will perceive it, but you feel it more like a shaking or a vibration, or if it's loud, you might just hear it as a series of clicks or bangs rather than an actual sound with a musical pitch. What does the frequency, that is the number of sloshes per second, have to do with the sound that we hear? Okay, and to understand that, it's probably best to just try it. I'll play you some sounds, and what I want you to do is listen to the sound, think about the pitch of the sound, and also watch the wave here. Okay, this is time along the bottom. So if the waves are squished up together, that means they're high frequency, they're coming often. And if the waves are stretched out apart, that means they're low frequency, they're coming less often to the microphone. All right, so let's make this sound. So we'll start again at low frequency. So that's a 140 hertz tone. You can see that the waves are nicely spread out. And now I'm going to increase the frequency, which means increasing the number of waves coming by each second. Now we're up to 600 hertz. You can see the waves are much more closely spaced together on the screen. So that's a higher frequency, more waves per time. And you'll also notice a higher note. I'll keep going a little bit. So there's 1200 hertz. You can see the higher frequency represented by the waves that are more closely spaced together. And again, we've gotten up to a much higher pitch. So what you'll notice is that as I turn down the frequency, the waves stretch out here and the note goes down. So the way we describe the pitch of the note is high for high frequency, low for low frequency. Okay, so we've definitely figured something out here, right? We've figured out that the frequency of the sound wave, the number of times it shakes per second, is what determines our perception of the pitch. So high pitch is high frequency. Okay, so we can do more than that with pitch. We can also think about how the frequency corresponds to the way that we commonly describe pitches. So musically, one of the most frequent intervals we talk about is the octave, right? So here's an octave. Right? And a musical octave corresponds to a doubling of the frequency. So if I start with 200 hertz and then I play 400 hertz, you'll hear those an octave apart. Or 800 and 1600, those are an octave apart. This shows you here the ranges of frequency for a lot of common instruments. So this goes down here from 10 hertz, which is just below what we can hear, up to 10,000 hertz. Remember, we can hear up to 20,000. You'll notice that the musical range that we use to play music actually consumes a good fraction of what we're possibly able to perceive. So we can hear from 20 hertz to 20,000 hertz, and we use, even just with the piano, most of that range. The piano goes from 27 hertz up to about 4,000 for the top note. Okay, the human voice, this includes sopranos, altos, tenors, basses, you name it. The human voice kind of runs from 100 about up to 1,000. Here's the tuba that my son plays, and the piccolo that no one in my household has attempted. Okay, so that gives you kind of a sense of the range that we have. Okay, and this is to show you again how frequency of the sound wave corresponds to the pitch that we hear. This is a low C on the piano, 262 hertz. Here's the octave above at 524, and you can see that's doubling like it should be. Okay, another common interval that we're used to musically is the musical fifth. So say from C to G, right? And that actually is also a simple interval. Here's the C, 262. Here's the G, 392. If you stare at that for a moment, you'll see that that G is 1.5 times the frequency of the C. Okay, so if you take a frequency, you multiply it by 1.5, you get the note that's a musical fifth above. And if you multiply it by 2, you get the octave. Here, right here at 440, is the A that the orchestra tunes to, right? So you may have heard people say, oh, we want A 440, right? 440 is describing the number of oscillations per second. So this is the A, the open A string on the violin. Okay, so we've said that, that how often the air is shaken by the instrument determines the frequency of the sound wave, and the frequency of the sound wave determines the pitch, the musical pitch that we hear. So it seems like the honest questions to ask at this point would be, what determines the frequency at which the instrument itself shakes, right? Because we know if the instrument shakes, it'll shake the air, that's all set. But what determines how fast the instrument will shake back and forth? Okay, so to think about that, I've brought actually my most ancient shaking thing. So this is a pendulum. Galileo loved these, and he thought about them by thinking about clocks. So pendula, heavy objects hanging from a string like this, always shake back and forth the same number of times each second. so long as you choose the same string and the same mass. So let's see if I can get it going. Right? You are getting very sleepy. Okay, so there's a pendulum shaking back and forth, and this has a frequency, right? It naturally goes back and forth all by itself a certain number of times a second, and I could make it start any day of the week, and it would always go back and forth the same number of times a second. Actually, everything has natural shaking frequencies like that. We call them resonances. So resonant frequencies are the natural vibration frequencies of an instrument or any object. A violin string or a guitar string, we think about what is going to actually, let's say, increase the pitch of the note that this string would play when you pluck it. Okay? So if we want to increase the pitch, we want to increase the frequency. And if we want to increase the frequency, we need to either increase the speed or decrease the length. So let's think about those two things separately. So you probably know that on a violin or on a guitar, if you want to go for a higher note, you put your finger down partway along the string, right? So that when you pluck it or you bow it, only a piece of it is sloshing back and forth, and that makes a higher note. It makes a higher note because it makes a higher fundamental resonant frequency, or lowest resonant frequency. But you know, if you did only that, life would be kind of hard, right? Because on a piano, for example, you have to be able to cover notes from about 27 hertz all the way up to 4,000 hertz, right? So that's a large range of frequencies. If you tried to do that just by having all the strings for the different notes just be different lengths, you would need the longest strings to be about 300 times the length of the smallest strings. So there'd be strings in there that were 1 centimeter long and strings in the piano that were 3 meters long, which would be inconvenient, right? 3 meters is, you know, whatever, 18 feet. Okay, so that doesn't fit. So what do they actually do in a piano? What's the difference between the low notes and the high notes? It is true that the strings are shorter for the high notes, but they're also skinnier, right? So if you look in there, there are those big, thick, heavy strings that are playing the low notes, and little skinny, light strings that are playing the high notes. Why does the mass make a difference? Well, you know that, because the mass tells us something about how fast a disturbance can propagate. Remember I said if we made these all really heavy, the wave would go up more slowly. So if we make things heavy, we decrease the velocity. Decreasing the velocity decreases the frequency. Okay, so we can change the pitch a string would play by making the string shorter. We could make the string lighter. That would make the pitch go higher. And then the final thing we could do, the final thing that goes into this velocity, remember, is the coupling between adjacent pieces, how much they talk to each other. And in a string, you make them talk to each other more strongly by pulling that string tighter, so that when you pull this piece, it exerts a bigger force on the piece next to it. And you know that too, so if you're tuning a violin and you wanted to make it higher, you tighten that string, you pull on it harder. Pulling on it harder increases the tension, that increases the velocity, that increases the frequency. Okay, so the mass, the tension, and the length all matter for the tuning of a string.